Welcome to the lesson on similarity. At the end of this lesson, you'll be able to identify similar figures and differentiate between congruent and similar figures. You will also be able to identify the conditions that define similarity of triangles and prove the basic proportionality theorem and its converse. You must be wondering why we're in a sports room during a geometry session. Well, there is geometry all around us. Let's try to find some here. Look at the different types of balls kept here. There's a football, a volleyball, a cricket ball, and a tennis ball. Ah, and here's a golf ball. That's quite a variety. All these balls are spherical in shape. Does this make them congruent? Objects are said to be congruent only if they are of the same shape and the same size. For example, look at these hockey sticks. They are equal in shape and size. Hence, they are congruent. As for the balls, though they are of the same shape, their sizes differ. Objects that are of the same shape but differ in size are said to be similar. Let's recap the definitions of congruent and similar objects. Congruent objects have the same shape and size, while similar objects have the same shape but may not necessarily have the same size. An important observation to note is that all congruent figures are similar, but all similar figures need not be congruent. Now, consider the geometrical figures given here. Let's sort the figures on the basis of similarity. Here, now all similar figures are aligned together. Let's analyze these figures to further understand similarity. All circles are of the same shape and their radii will always be proportional. Hence, all circles are similar. All squares are similar to each other as their angles are equal and their corresponding sides are proportional. Using the same logic, all rectangles are similar as the angles are equal and two pairs of corresponding sides are proportional. Now, let's check the similarity of triangles. On measuring the angles, we find that the corresponding angles are equal. On measuring the lengths of the corresponding sides, we find that the three pairs of corresponding sides are proportional. For two triangles to be similar, the corresponding angles must be equal and the length of the corresponding sides must be proportional. To better understand the property of the similarity in triangles, let's perform a small activity. Cut a triangular-shaped piece of cardboard. Let's call this triangle ABC. Now hold it between a light bulb and the wall. Can you see the shadow of the triangle? It is an enlargement or magnification of the cardboard triangle because light propagates in a straight line. Let's mark the shadow of the triangle as A', B', C'. Consider the point of the light bulb as O. Draw rays OA, OB and OC originating from point O. If we extend this ray further, we'll observe that A' lies on ray OA, B' lies on ray OB, and C' lies on ray OC. This means that the triangles ABC and A', B', C' are of the same shape. However, their sizes are different. So we can say that triangle ABC is similar to triangle A-B-C- and vice versa. Mathematically, similarity is represented as shown. Here, vertex A corresponds to vertex A', vertex B corresponds to vertex B', and vertex C corresponds to vertex C'. Symbolically, these correspondences are represented as A', B', B', and C'. Similarly, angle A is equal to angle A', angle B is equal to angle B', and angle C is equal to angle C'. And all pairs of corresponding sides of the triangles are proportional. Note that the same ratio of the corresponding sides is referred to as the scale factor. Next, we will discuss an important theorem based on the similarity of triangles. This theorem is called the basic proportionality theorem or the Thales theorem. The basic proportionality theorem states that if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then the other two sides are divided in the same ratio. A triangle ABC is given such that a line drawn parallel to side BC intersects the other two sides AB and AC at points D and E respectively. If we prove that AD upon DB is equal to AE upon EC, then the theorem will also be proved. To prove this theorem, join B to E and C to D. Also draw two perpendiculars, DM on AC and EN on AB. Let's begin the proof. Consider triangle ADE and triangle BDE. The area of a triangle can be calculated as half of the product of the base and the corresponding height. This means the area of triangle ADE is half the product of the base AD and the height EN. Similarly, the area of triangle BDE is half the product of the base DB and the height EN. Now, let's divide the areas of the two triangles. On simplifying, we can see that the area of triangle ADE divided by the area of triangle BDE is equal to side AD divided by side DB. Let's assign this observation as equation 1. Now consider triangle ADE and triangle DEC. The area of triangle ADE can also be calculated as half the product of the base AE and the height DM. The area of triangle DEC is equal to half the product of the base EC and the height DM. Now, let's divide the areas of the two triangles. We can see that the area of triangle ADE divided by the area of triangle DEC is equal to AE divided by EC. Let's assign this observation as equation 2. Consider triangle BDE and triangle CED. The area of triangle BDE is equal to the area of triangle CED because these triangles are on the same base DE and between the same parallels BC and DE. Let's assign this observation as equation 3. From equations 1, 2 and 3, we get the following expression. This implies that the ratio of sides AD and DB is equal to the ratio of sides AE and EC. Thus, the basic proportionality theorem is proved. Now, let's prove the converse of the basic proportionality theorem. The converse of the theorem states that if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Consider the figure. A triangle ABC is given. The line DE intersects side AB and AC at points D and E respectively, such that the sides are divided in the same ratio. To prove the theorem, we'll prove that line DE is parallel to side BC. In triangle ABC, AD upon DB is equal to AE upon EC, because it is given that line DE intersects the sides AB and AC in the same ratio. Let's assign this observation as equation 1. Let's assume that DE is not parallel to BC. If DE is not parallel to BC, draw a line DE' parallel to BC. Since DE' is parallel to BC, by the basic proportionality theorem, we have AD by DB is equal to AE' by E'(C). Let's assign this observation as equation 2. From equations 1 and 2, we get AE by EC is equal to AE' by E'(C). Let's assign this observation as equation 3. Adding 1 on both sides of 3 and on simplifying, we get EC is equal to E'(C). Therefore, we can say that E and E' coincide. Hence, DE is parallel to BC. Lila is in Egypt on an exchange program sponsored by her school. Everything about Egypt is magnificent, and the pyramids that the Egyptians built around 2500 BC are just mesmerizing. It looks like the Egyptians knew a lot about geometry. How else could they have made such huge similar structures? What amazes her most is the similarity between the pyramids. Now, look at the lateral surfaces of all the pyramids. They are all triangles that are similar to each other. Welcome to the lesson on the criteria for the similarity of triangles. At the end of this lesson, you will be able to prove the AAA, the SSS, and the SAS similarity criterion of triangles. Let's consider two triangles, triangle ABC and triangle DEF. These two triangles are similar. Recall that for two triangles to be similar, two conditions must be met. First, the corresponding angles of the two triangles must be equal. Second, the corresponding sides of the two triangles must be proportional. Now, to prove the similarity of triangles, do we need to prove both the conditions? Actually not. There are three criteria that define the similarity of triangles. These are the AAA, the SSS, and the SAS similarity criteria. Proving any of these criteria is enough to prove that two triangles are similar. Let's discuss these criteria in detail. By the AAA similarity criterion, if the corresponding angles of two triangles are equal, then their corresponding sides are proportional and the triangles are similar. Let's consider two triangles, triangle ABC and triangle PQR. Here angle A is equal to angle P. Angle B is equal to angle Q. And angle C is equal to angle R. In order to prove that triangle ABC is similar to triangle PQR, by the AAA similarity criterion, we'll prove that the ratios of sides AB and PQ, AC and PR, and BC and QR are equal. To prove the criterion, we'll mark 2 points, L and M on PQ and PR respectively, such that PL is equal to AB and PM is equal to AC, and then we'll join LM. Now, let's consider triangle ABC and triangle PLM. In these two triangles, by construction, AB is equal to PL and AC is equal to PM. Also as given, angle BAC is equal to angle LPM. Therefore, by the SAS congruence rule, triangle ABC is congruent to triangle PLM. Now, let's consider angle B and angle L. These two angles are equal as they are corresponding angles of congruent triangles. It is also given that angle B is also equal to angle Q. Hence, angle L is equal to angle Q. Now, let's consider LQ. Observe that it forms a transversal to LM and QR. Since angles L and Q form a pair of corresponding angles that are congruent, LM is parallel to QR. Next, let's consider sides PL and LQ and sides PM and MR. By the basic proportionality theorem, PL upon LQ is equal to PM upon MR. That means these sides are proportional. Now, let's take the reciprocal of this equation. Let's add 1 to both sides of the equation and simplify it. Here LQ plus PL is equal to PQ and MR plus PM is equal to PR. Through construction, PQ and AB are in the same ratio as PR and AC. Now, let's take the reciprocal of this equation. We'll call this equation 1. Similarly, AB and PQ are in the same ratio as BC and QR. Let's call this equation 2. Equating 1 and 2, we get the ratio of AB and PQ equal to the ratio of AC and PR, which is equal to the ratio of BC and QR. Thus, we have proved both the conditions for the similarity of triangles. Hence, triangle ABC is similar to triangle PQR. We have proved that if the corresponding angles in two triangles are equal, then their corresponding sides are in the same ratio and the triangles are similar. This is the AAA similarity criterion. An important point to note is that when two corresponding angles of two triangles are equal, then the two triangles are similar. This is referred to as the AA similarity criterion. The converse of this theorem defines the second similarity criterion, the SSS similarity criterion. We'll discuss it next. By the SSS criterion, if the sides of one triangle are proportional to the sides of the other triangles, then their corresponding angles are equal and the triangles are similar. Let's consider two triangles, ABC and DEF. Here the ratios of the corresponding sides are equal. In order to prove that the two triangles are similar, we'll prove that the corresponding angles are equal. To prove this criterion, we'll mark 2 points, P and Q, on DE and DF respectively, such that DP is equal to AB and DQ is equal to AC, and we'll join PQ. Let's consider triangle ABC and triangle DEF. It is given that the ratio of AB and DE is equal to the ratio of AC and DF. Now, by construction, DP is equal to the side AB and side DQ is equal to the side AC. Taking the reciprocal, we can also write the equation as DE upon DP is equal to DF upon DQ. On subtracting 1 from both sides of the equation and simplifying, we get PE upon DP is equal to QF upon DQ. Now taking the reciprocals again, we get dP upon PE is equal to dQ upon QF. By applying the converse of the basic proportionality theorem, PQ is parallel to EF. Since PQ and EF are parallel, angle P is equal to angle E and angle Q is equal to angle F, as they form a pair of corresponding angles. Now, dP upon dE is equal to dQ upon dF, which is equal to PQ upon EF. This can also be written as AP upon DE is equal to AC upon DF, which is equal to PQ upon EF. But AB upon DE is equal to AC upon DF, which is equal to BC upon EF. Therefore, PQ upon EF is equal to BC upon EF. Hence, BC is equal to PQ. In triangles ABC and DPQ, by construction, AB is equal to DP and AC is equal to DQ. Therefore, we will be able to prove that BC is equal to PQ. Hence, triangle ABC and triangle DPQ are congruent by the SSS congruence rule. So now angle A is equal to angle D, angle B is equal to angle P, and angle C is equal to angle Q. Since angle P is equal to angle E and angle Q is equal to angle F, angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle F. Therefore, triangle ABC is similar to triangle DEF. We have proved that if the sides of one triangle are proportional to the sides of the other triangles, then their corresponding angles are equal and the triangles are similar. Thus, the SSS similarity criterion is proved. Next, we'll discuss the SAS similarity criterion. By the SAS similarity criterion, if one angle of a triangle is equal to one angle of the other triangle, and the sides including these angles are proportional, then the triangles are similar. Let's consider two triangles ABC and DEF. Here it is given that angle A is equal to angle D, and AB upon DE is equal to AC upon DF. We will prove that triangle ABC and triangle DEF are similar. Let's mark 2 points P and Q on DE and DF respectively, such that the side DP is equal to the side AB and side DQ is equal to the side AC, and we'll join PQ. It is given that the ratio of side AB and DE is equal to the ratio of side AC and DF. Since DP is equal to AB and DQ is equal to AC, this equation can also be written as DP upon DE is equal to DQ upon DF. Now, let's take the reciprocal of this equation. Next, DE can be written as the sum of DP and PE, and DF can be written as the sum of DQ and QF. On simplifying, we get. Now, taking reciprocals again, we get dP upon PE is equal to dQ and QF. By the converse of the basic proportionality theorem, PQ is parallel to EF. Since PQ and EF are parallel, angle P is equal to angle E, and angle Q is equal to angle F, because they are corresponding angles. Now consider triangle DPQ and triangle DEF. Since angle P is equal to angle E, and angle Q is equal to angle F, triangles DPQ and DEF are similar. Let's call this equation 1. In triangle ABC and DPQ, AB is equal to DP and AC is equal to DQ by construction. It is given that angle A is equal to angle D. Therefore, by the SAS congruence rule, triangle ABC and triangle DPQ are congruent. Let's call this equation 2. From equations 1 and 2, we get triangle ABC is similar to triangle DEF. You have reached the end of this section. Before moving on, let's review the key points covered. Two triangles are similar if their corresponding angles are equal and their corresponding sides are in the same ratio or are proportional. If in two triangles the corresponding angles are equal, then their corresponding sides are proportional and the triangles are similar. This criterion is referred to as the AAA, or the angle-angle-angle similarity criterion of triangles. If two corresponding angles of two triangles are equal, then the two triangles are similar. This is known as AA, or the angle-angle similarity criterion of triangles. If in two triangles, the sides of one triangle are proportional to the sides of the other triangle, then their corresponding angles are equal and the two triangles are similar. This criterion is referred to as the SSS, or the side-side-side similarity criterion of triangles. If one angle of a triangle is equal to one angle of the other triangle, and the sides including these angles are proportional, then the two triangles are similar. This criterion is referred to as the SAS, or the side-angle-side similarity criterion of triangles. Hope you enjoyed this learning experience. Welcome to the lesson on the areas of similar triangles. At the end of this lesson, you will be able to prove that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. You will also be able to prove that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both sides of the perpendicular are similar to the whole triangle and to each other. You will also be able to prove the Pythagoras theorem and its converse. In this lesson, we'll discuss three important theorems that are based on the areas of similar triangles. But first, let's review the basics of similar triangle. Consider this scenario. It is mid-morning and Stan and Anita are waiting for their friends in the park. They're both standing beside a lamppost. Stan is getting bored, so he begins quizzing Anita. If the length of Anita's shadow and the length of the shadow of the lamppost are known, can the actual length of the lamppost be calculated? Anita's shadow measures 10 feet, while her actual height is only 5 feet. The shadow of the lamppost is 30 feet. Let's assume that the height of the lamppost is x. If you observe the positions of the lamppost and Anita, they are both standing vertical to the ground. Both form a right angle with the ground, in other words, are perpendicular to the ground. The rays of the sun passing through the lamppost and Anita make a common angle and also define the lengths of their shadows. As you can see, two triangles are formed. Now, are these triangles similar? In the two triangles, we have two pairs of corresponding angles equal. Hence, by the AA criterion of similarity, the triangles are similar. Recall that the sides of similar triangles are proportional. Taking the ratio of the sides, we get the equation 5 divided by 10 is equal to x divided by 30. On simplifying, we get x is equal to 5 multiplied by 30, the whole divided by 10, which is equal to 15. Therefore, the length of the lamppost is equal to 15 feet. Remember, when two triangles are similar, their corresponding angles are equal and their corresponding sides are proportional. But what about their areas? Will the areas be equal, or will they be proportional? To answer these questions, let's discuss the first theorem. The first theorem states that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Consider triangle ABC and triangle PQR. It is given that these two triangles are similar. we will prove that the ratio of the areas of triangles ABC and PQR is equal to the square of the ratios of their corresponding sides AB, PQ, BC, QR, and CA, RP. To begin with, let's draw altitudes AM and PN on sides BC and QR respectively. Consider triangle ABC. Its area is equal to half the product of the base BC and the altitude AM. Similarly, the area of triangle PQR is equal to half the product of the base QR and the altitude PN. Now, let's take the ratios of the areas of the two triangles. On further simplification, the equation obtained is as shown here. Let's assign this as equation 1. This implies the ratio of the areas of triangle ABC and PQR is equal to the product of BC divided by QR and AM divided by PN. Now, let's consider the triangle ABM and triangle PQN. Angle B is equal to angle Q, as they are corresponding angles of similar triangles ABC and PQR. Angle AMB is equal to angle PNQ, as both angles measure 90 degrees. Thus, by the AA criterion, triangle AMB is similar to triangle PNQ. This also means that sides AM and PN are in the same ratio as sides AB and PQ. Let's assign this as equation 2. We know that triangle ABC and triangle PQR are similar. Therefore, we can say that their corresponding sides are in the same ratio. Let's assign this as equation 3. Now, recall equation 1. By applying equation 3, we can replace BC upon QR with AB upon PQ. Similarly, applying equation 2, we can also replace AM upon PN with AB upon PQ. Thus, we have proved that the ratio of the areas of triangles ABC and PQR is equal to the square of the ratio of sides AB and PQ. Please note, side AB and side PQ are corresponding sides of the similar triangles ABC and PQR. We can similarly prove for the other pair of corresponding sides BC, QR, and CA, RP. Hence, we have proved the theorem, which states that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Now, let's look at another important theorem, which states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Consider a right triangle ABC. It is given that angle B is the right angle and BD is perpendicular to the hypotenuse AC. Here, we will prove that triangle ABC, triangle ADB, and triangle BDC are similar. In triangles ADB and ABC, angle A is common. Similarly, angle ADB is equal to angle ABC as both are 90 degrees. Therefore, by the AA criterion of similarity, triangles ADB and ABC are similar. Let's assign this as observation 1. Similarly, we can prove that triangle BDC is similar to triangle ABC. Let's assign this as observation 2. From observations 1 and 2, we can conclude that triangle ADB is similar to triangle BDC. This also implies that the two triangles ADB and BDC are similar to triangle ABC. Thus, we've proved the theorem, which states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Next, we'll apply this theorem to prove another theorem, the Pythagoras theorem. Let's recall the Pythagoras theorem. It states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Triangle PQR with the angle PQR equal to 90 degrees is given. We need to prove that the square of the hypotenuse PR is equal to the sum of the squares of the other two sides PQ and QR. Now, let's draw a perpendicular from the vertex Q to PR. Name it QS. The perpendicular QS divides the side PR into PS and SR. We now have two triangles, RSQ and PSQ. Consider the triangles PQR and PSQ. Here we can see that the angle P is common to both triangles. Thus, angle QPR is equal to angle SPQ. Similarly, angle PQR is equal to angle PSQ, as both the angles are equal to 90 degrees. By the AA criterion of similarity, we know that if two angles of one triangle are equal to two angles of another triangle, then the two triangles are similar. Hence, the triangle PQR is similar to triangle PSQ. Since the two triangles are similar, corresponding sides are proportional. Hence, side PQ divided by PS is equal to side PR divided by PQ. By simplification, we get PQ square is equal to PR multiplied by PS. Let's assign this as 1. Now, looking at triangles PQR and QSR, we can see that angle QRP is equal to angle QRS. Also, angle PQR and angle QSR are equal to 90 degrees. Again, by the AA similarity criterion, we know that triangle PQR is similar to triangle QSR. So we know that the corresponding sides are proportional. On simplification, we get QR square is equal to PR multiplied by SR. Let's assign this as observation 2. Now, adding the equations 1 and 2, we get PQ square plus QR square is equal to the product of PR and PS plus the product of PR and SR. From the figure, we get PS plus SR is equal to PR. Hence, we get PR square is equal to PQ square plus QR square. In other words, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Thus, the Pythagoras theorem is proved. Now, let's prove the converse of the Pythagoras theorem. The theorem states that if the square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle. We have a triangle ABC in which AC square is equal to AB square plus BC square. We need to prove that angle B is equal to 90 degrees. Let's construct a right triangle PQR with a right angle at Q such that PQ is equal to AB and QR is equal to BC. By the Pythagoras theorem, in triangle PQR, PR square is equal to PQ square plus QR square. This is because angle Q is equal to 90 degrees. By construction, we know that the corresponding sides of triangles ABC and PQR are equal. Thus, PR square is also equal to AB square plus BC square. Let's assign this as observation 1. We know that AC square is equal to AB square plus BC square. Let's assign this as observation 2. From observations 1 and 2, we get AC is equal to PR. Let's assign this as observation 3. Now, in triangle ABC and PQR, AB is equal to PQ and BC is equal to QR by construction, and AC is equal to PR from observation 3. Therefore, by the SSS criterion for congruence, triangle ABC is congruent to PQR. Angle B is equal to angle Q by the corresponding parts of congruent triangles, and the angles Q and B are equal to 90 degrees by construction. Thus, the theorem is proved. You have reached the end of this section. Before moving to the next section, let's review the key points covered. The ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. If a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. The Pythagoras theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The converse of the Pythagoras theorem states that in a triangle, if the square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle. Hope you enjoyed this learning experience.